we just got started on what the difference was between covalent bonds and ionic bonds. And when we started learning about electronegativity, realized that the difference in electronegativity between two atoms that were sharing electrons, the bigger the difference in electronegativity, the more time those electrons spent toward the more electronegative element. And if the difference was so great, the electron would spend so much time closer to the more electronegative element that it would just keep it and become negatively charged. So let's have a look at how that worked. So when we have a pure ionic compound, basically there's no sharing of electrons at all. And what we have to realize is that sometimes it's sort of a gradual change, in that we would say that a polar covalent bond, we say has some ionic character. And why do we say it has some ionic character? Well, the character of an ionic bond is that it's charged, right? So we have a charge here, and we have a charge there. But notice with a polar covalent bond, we have a partial charge here, so the one with lower electronegativity, and we have a partial negative charge here for one that has higher electronegativity. And the greater the difference, the greater that partial charge will be. So we say that this has ionic character. So ionic character. And the greater that difference, the more ionic character it has, until it has so much ionic character that it basically becomes ionic, and that partial charge becomes a complete charge. On the other hand, as you move away, as the difference in electronegativity gets smaller and smaller and smaller, we get less and less ionic character and more covalent character, until you get down here at the end, where you see a compound that basically has no difference in electronegativity, or a very, very small difference in electronegativity. Then you would see that pair of electrons being shared evenly, so that the electron distribution would be just the same on this side of the molecule as it is on this side of the molecule. Basically, the same amount of electrons would be seen all over the molecule, and so there wouldn't be any polarity. Polarity comes from when there's more electron density on one side of the molecule than the other. In a polar covalent molecule, there's greater electron density. There's greater electron density on this side. There's more electrons on that side of the molecule than on this side. And so we say this is polar. There's a greater electron density on the right side, so it's somewhat negative. And on the right side is somewhat lower electron density, so we say it's somewhat positive. But when that density is equally shared on both sides, we have a completely non-polar covalent bond, meaning it's completely even all the way around, and there's no charge distribution whatsoever on a bond like that. And so that would be most of the gases we see. Cl2 is a gas, H2 is a gas, O2 is a gas, F2 is a gas. They're gases because they're very non-polar. You need something to be polar for it to become a liquid. Something completely non-polar tends to be a gas, because there's nothing for it to have this difference in charge that keeps things stuck together. When something's completely non-polar, there's nothing keeping these molecules stuck to one another, so they just float off. So most gases are going to be completely covalent, non-polar bonds. So now we're going to talk about oxidation numbers. We know that different elements can be charged. right? I mean, metals can be charged. We know that. And so we say that, like iron, for instance, can be +2 or +3. So if it loses 2 electrons, and remember, it loses them completely. It doesn't get them back. So it becomes +2. If it loses 3 electrons completely, it becomes +3. But what about if an element is sharing electrons with another element? Yes, is there a question? Okay. Excuse me. Can you still hear me?
Yeah, you're good.
Yeah, I saw my screen freeze up, and it's like, uh-oh. So, yeah, we're going to have to get used to that, I guess. So if you have two atoms that are sharing electrons, but they're not being nice, and one of them has a much higher electronegativity and is pulling those electrons away from the other atom, we say that we assign it an oxidation number. Meaning, if it was sharing them evenly, we'd give it an oxidation number of 0. If it was completely nice and sharing them. So the more electronegative atom, we just give it all the shared electrons. Like for instance, if hydrogen is forming a bond with fluorine, we know the fluorine's the most electronegative element. So it's sharing these 2 electrons, right? Remember, each bond is a pair of shared electrons. So since fluorine is so electronegative, it's the Mac Daddy of electronegativity, it steals basically both of these electrons. So we give them both to fluorine. And so we'd say fluorine now has 1 more electron than now it has 8 electrons in its outer shell rather than 7. So we give it an oxidation number of -1. And hydrogen now has no electrons rather than the 1 it normally has, and we give it an oxidation number of +1. Okay? That's basically how that works. So the less electronegative atom gets none of the shared electrons. Each atom, if they have unshared electrons, each atom gets to keep those because they're not sharing them. So those are valence electrons that are not being shared, and so the less electronegative atom gets to at least claim it has those. But anything shared goes to the more electronegative. And so to figure it out, we have a equation. So our oxidation number is the number of valence electrons that an element has. So in this instance, with HF, F would have 7. And then we subtract the number of shared electrons, that would be 2, and the number of unshared electrons, wait a minute, unshared electrons, that would be 6. It keeps 6 for itself. So of those 7 valence electrons, it was sharing 1 of the 7, and it's keeping both of the shared electrons, the one it was sharing and the one that hydrogen was sharing. So we go 7 minus 2 plus 6, that's 7 minus 8, so that's where you get the -1. We'll do a lot more of these. It'll make more sense. Basically, what the oxidation number tells you that if this was an ionic compound, this is what the charges would be. And basically why we use it, because it shows us where the electrons go when a reaction takes place. Now, one of the classic ways we know that electrons move around is when something is oxidized, when something's reacted with oxygen. Generally, those shared electrons go to oxygen because it's very electronegative. And so oxygen generally has an oxidation number of -2 because it keeps the 6 electrons, or it keeps the 5 electrons now I'm getting all confused. It has 6 electrons it's sharing 2, and it basically keeps the other 2 pair. So now it has 8 when it normally has 6. So we say it has 2 more, and we give it a charge of -2. Now this isn't a formal charge. We will learn the difference between a formal charge, where something actually has a charge on it, and an oxidation number, meaning it's stealing those electrons, but it's not keeping them entirely. So we'll learn about the differences in a minute. And here's the HCl rather than HF. So chlorine, also more electronegative than hydrogen. Hydrogen has an electronegativity of around, if I remember correctly, around 2.1. And chlorine has an electronegativity of 3. And so chlorine is going to keep more of those electrons. So it has 7 valence electrons. It's sharing 2. That's a single bond, remember, is always 2 electrons. If it has 2 bonds, that's 4. If it has 3 bonds, that's 6, and so on. So it has 7 valence electrons. It's sharing 1 of them, and so it has 6 that it keeps to itself. And we do that same equation that I showed you before. Here's its 7 valence electrons. It's keeping 2 of them, and it has 6 by itself. So we say it's got an electronegativity or an oxidation number of -1. And since hydrogen just has 1 electron and loses it, we say it's +1. Any questions about that? I know it's sort of a new concept, but you'll see why it's important as we go along. It basically is the covalent bonds way of keeping tabs on who's getting the electrons and who isn't. In an ionic bond, we know who's keeping the electrons and who isn't because they're charged. We can easily see it. But in a covalent compound, sometimes it's not so easy to see where exactly the electrons are going. And so we use oxidation numbers to basically tell us where's the higher electron density going to be. And so we look and see wherever the negative numbers are, that's where the higher density of electrons are going to be, and lets us figure out which ones are polar and which ones are non-polar. And that's pretty much one of the main themes of the entire. Rick, you're with us.
That's good.
Good, man. Yeah, so this basically one of the main themes of the whole chapter is trying to figure out which molecules are polar, which molecules are non-polar. So this is another way of showing which bonds are polar and which ones aren't. So one way that we sort of showed you already is we have this little symbol where we make a delta like that and just give it a minus or a plus. And that, remember, that means partial. This delta symbol means partial. It means it's not a complete charge. It's less than 1. More than 0, less than 1. It means that this has more electrons on that side of the bond. This has fewer electrons on that side of the bond. The other way that we show it, especially when we're drawing these compounds, and you're going to be doing a lot of drawing of these compounds, these molecules, is to have an arrow like this. Now, it points to which element is more electronegative. So basically, remember that this cross here sort of stands for which one's more positive. That's the way I remember it anyway. So when you make that cross, you say this one, because it looks like a positive, right? That side is a little more positive, and you're pointing to where the electrons are going. So in this instance, we know the electrons are going to be moving towards fluorine because fluorine is hella electronegative, right? So that's where the electrons are going to spend. The shared electrons are going to spend more of their time. And so this helps us, this particular symbol also helps us determine which molecules are polar and which molecules are not polar. And it's with just 2 atoms, a diatomic molecule, it's pretty easy to see if they're polar or nonpolar, right? I mean, you just see, does it have an arrow? Oh yeah, it does. Done. It's polar. It gets a lot more complicated when you have compounds that have 4, 5, 6, 10 different bonds, and then you have to look at how are these arrows organized. If they're all pointing in the same direction, then it's polar. If they're pointing in exactly opposite directions, it's not. And let me give you an example. If you have like carbon dioxide, everyone's familiar with carbon dioxide, this is what it looks like. So let me draw it for you. So we have carbon in the middle, and we have a double bond to oxygen on that side, and a double bond to oxygen on this side. And oxygen has 1, 2, 3, 4 electrons that it keeps for itself. Carbon has carbon generally does not keep any electrons to itself. It likes to share all 4. So that's what carbon looks like. And it's completely linear. It's completely linear. And carbon has a lower electronegativity than oxygen. Yeah, remember, oxygen is has the second highest electronegativity of any element. So it's generally going to be more electronegative than everybody. And so if we were to draw the arrows to show us polarity, one would be going in that direction, and the other would be going in this direction. So we have 2 polar bonds. Each of those carbon-oxygen double bonds is polar. Oxygen is keeping more of the electrons. That is a polar bond. But each of those polar bonds is in exactly the opposite direction. So it's an orientation of these bonds that determines whether or not the whole molecule is polar. So we can have 2 polar bonds in a nonpolar molecule because they're equal and opposite. And so that's why carbon dioxide is a gas. Because remember, I told you the gases are going to be nonpolar molecules. They're all nonpolar molecules. So even though carbon dioxide has like really polar bonds, it has 2 of them oriented in exactly opposite directions. And so that's what makes it nonpolar, and that's what makes it a gas. Any questions about that? We're going to talk more about it in a little while. I sort of figured it was a good chance to introduce that concept. Nothing? I'm just going to keep babbling then. Okay.
Oh, wait, Professor.
Yep, sure.
Is there a particular reason, is there a particular preference over which method is being used here in terms of the arrow or the delta sign?
We generally use the arrow. That's a really good question. We generally use the arrow when we're dealing with a molecule that has more than 1 bond in it. Like, for instance, water. Oh dear, what the hell is that? There we go. Let me draw a little something here. Okay, so here's what water looks like. And believe me, I'm going to spend a lot of time on water. Water looks like this. So it shares a pair of electrons with this hydrogen and a pair of electrons with this hydrogen. And as I remember, oxygen usually keeps 2 pair of electrons. We call those lone pairs. It keeps 2 pair of electrons to itself. Now, the reason it's bent is because we have these lone pair of electrons, which are negatively charged, and they keep apart from each other, and they keep the hydrogens from interacting with them. And so we have this bent shape. It's not linear like carbon dioxide is. And so we use the arrows pointing in this direction. So oxygen is more electronegative than hydrogen. So now we have two arrows depicting polar bonds. We now have 2 polar bonds again, but they're pointed in the same direction, not opposite direction. If they were equal and opposite, it would be nonpolar, but they're not. They're both pointing up. And so we have a net polarity pointing up. And so it's in those sort of situations where we prefer to have the arrows. Generally, we only use these when we have like diatomic molecules. But yeah, it's a really good question. So I generally just use the arrows. But you can
Thank you.
use the, yeah, no worries, man. Good question. So now we're going to look at the electron density, because basically that's what I've been nattering about. The difference in polarity means the electron density. If it's more towards one atom, it's going to be polar. If it's evenly distributed between both, it's nonpolar. And this sort of shows you exactly what I'm talking about. So here we have H2. Here we have hydrogen gas. And you can see if we look at the distribution of electrons, we're looking at the density of electrons. And you remember when we talked in the last chapter, when we talked about the s orbital. So we had our nucleus, right? And then we had the s orbital. And it was sort of looked like this. It had a distribution. This is basically where you're going to find the electrons in an s orbital. They're going to be sort of distributed around the nucleus. So if we look for them, you can see where these peaks are near the nucleus. Not completely near the nucleus, but most of the time the electrons are near the nucleus. And so you can see that with the H2, it's even. This side is the same as that side, nonpolar bond. Now let's look at fluorine, F2. Now these distributions are higher because there's a lot more electrons. Hydrogen's only got 2, and fluorine's got 9. So a lot more electrons. That's why these peaks are a lot higher. But you can see that they're exactly the same. This one is exactly the same as that one. So the distribution on one side of the molecule is exactly the same as the distribution on the other side. Again, nonpolar. And it's a gas. H2 is a gas. F2 is a gas. And then we get down to HF. So now hydrogen's bonding with fluorine, and it ain't equal. Notice there's a lot more electron density on one side of that molecule than the poor hydrogen hardly has any density at all. So fluorine is just really pulling all the electron density toward itself. And this is a polar molecule. Basically, this is an acid that's soluble in water, whereas these two are gases. Okay, so does this make sense? You sort of, it gives you like a visuals. What do these electron densities actually look like? And if they're equal, nonpolar. If they're not equal, it becomes polar. So as I mentioned previously, it's that difference. It's that difference in electronegativity that tells you what kind of bond you're dealing with. And so at 0, when I've got 2 atoms who are identical, or 2 atoms that have identical electronegativities, it's completely nonpolar. There's no polar character to it whatsoever, because my difference is 0. So one element is pulling on those electrons exactly as hard as the other element is. Those atoms are pulling on those electrons evenly, so they're evenly distributed. When we get up to a difference of around 0.4 or so, and that's basically the difference between carbon and hydrogen, that's still nonpolar. I think, if I remember, carbon is 2.5, and hydrogen is 2.1. So this difference is 0.4. And we signify the difference by delta, that means difference, and En. So the difference in electronegativity is 0.4. So we still consider this a nonpolar covalent bond. But once the difference starts to rise above 0.4, like 0.5 and above, then we call it a polar covalent bond. That's where we get things like HF and water, OH, that sort of thing. Those are polar covalent bonds. And eventually the difference becomes so great that we say, well, this is mostly ionic. When you get above 3.3, it's completely ionic. But pretty much anything between 1.7 and 3.3, we say has a lot of ionic character. And the higher, the more ionic it is, until it becomes completely, like when we have a metal and a non-metal, basically all of those differences are greater than 1.7. Any questions about that? This is really the only way we measure ionic character. Above 0.4 and above, we say it's polar, and then 1.7 and above, we say it's ionic. But you can see it's the CH bond. We sort of left the bar at 0.4 because it's the CH bond that's involved in so much, like, oils and lipids and fats and, all of these sort of, important biological molecules that we know about them as being non-polar. And the difference between carbon and hydrogen is 0.4. So I think that's probably why that is the basis for whether or not we consider a bond to be polar or not, okay? So that's why hydrocarbons are so non-polar. So let's look at a couple of these. So we're using that polar arrow we mentioned before. So this one, we're going to look at nitrogen-hydrogen bond, a fluorine-nitrogen bond, and an iodine-chlorine bond. Then rank which one of these bonds is the most polar. Hydrogen-nitrogen, hydrogen-oxygen, or hydrogen-carbon. I think you can probably figure out which one that one is, okay? So let's have a look. So here's our electronegativities. So here's the ones we were interested in, right? Here's iodine, that's 2.5. Chlorine is 3. Fluorine is 4. Carbon's 2.5. I'm not going to force you to remember these. You can always have a table. Hydrogen's 2.1. And I think that was, nitrogen. Nitrogen's 3. So nitrogen's tied with chlorine for the third most electronegative. All right, so let's have a look. So we would say that nitrogen, a lot more polar than hydrogen. That makes sense. So we would draw the arrow like that. However, remember, fluorine, that's the easiest thing to remember. Fluorine is hella electronegative. It's the most electronegative. You bond that to anything. It doesn't matter what it is. And the arrow is going to always points towards fluorine. And then remember, one of the rules we learned about, as the atom gets bigger, it becomes less electronegative, because once the atom gets bigger and bigger and bigger, it's harder for the nucleus to pull on all of those electrons. And so iodine and chlorine are both halogens. They're both in group 7. They both become ionic. They both become -1. But chlorine is smaller. And so it's better able to pull electrons away from other elements. And so it pulls electrons even away from iodine. So then here, since carbon had electronegativity of 2.5, and nitrogen had an electronegativity of 3, and oxygen had an electronegativity of 3.5, this one's going to be the most polar. And a lot of times we need to look at which bonds are more polar than others. We may have, in certain molecules, some bonds that are like really polar, and then some bonds which are less polar. And when we're trying to figure out which way the polarity goes, it would point towards the bonds which are the most polar. Okay, So this will give you an idea of sort of what happens as you reduce the electronegativity difference of the bonds you're making. It makes a big difference, because I've sort of been harping on the fact that the periodic table has all of these different, periodic properties. One of them is electronegativity and size and everything, charge and everything else we've been looking at. The electronegativity difference makes a huge change in these particular compounds. And we can look at it this way. These are all chlorides. All of these compounds you see before you are chlorides. And basically, we're just going to start with period 3 and just go all the way across the table, okay? Question? Okay, so we're going to start basically with sodium. So sodium we know is element 11, right? Element 11, element 12, 13, 14, 15, 16, till we get to 17. We're just moving across the periodic table. And you remember that metals have very low electronegativities, and as we move across the table toward the nonmetals, the electronegativity increases, right? So the atoms get smaller and smaller and smaller. The electron clouds get smaller and smaller and smaller as we move across the periodic table. And the electronegativity goes up as the atoms get smaller and smaller and smaller, because it's easier to pull those electrons in towards the nucleus. So let's look at the difference. So we start with sodium, which is a really low electronegativity. So this difference is huge between chlorine and sodium. That's an ionic bond, and it forms an ionic solid. NaCl forms an ionic solid, and it melts at around 800 degrees, and it's very conductive when it melts. Makes sense because it's ionic. What happens when we react chlorine with magnesium? Magnesium's another metal. Also has a big difference. Let me clear this out. It also has a big difference in electronegativity, around 1.8 or so. So it is also an ionic solid. It also melts at a high temperature, and it's also conductive. Well, so far, not too surprising. But let's look at aluminum. The difference in electronegativity of aluminum and chlorine is less. It's now only about 1.5 difference. That's right on the border of whether something's ionic or polar covalent. And notice, look at the difference in the compound. Sodium crystals are really big. Everyone knows what sodium chloride crystals are. They look really, really big. Notice that the crystals in magnesium chloride are smaller. And then when we get to aluminum, it's almost a powder, right? Those crystals are really, really small, because we're getting to the point where that bond is kind of ionic and it's kind of polar covalent too. It has a lot of properties of both of them. And you can see that. Look at the difference in the melting point. Melting point drops from like 700 degrees all the way down to less than 200. So that aluminum chloride will melt before water boils. No, actually, a little higher than water. Sorry, that's Celsius. Yeah. So yeah, only around 200 degrees though, that'll melt, which is much, much lower than an ionic solid generally is. Now we move over one more. Now we've got silicon chloride. Silicon chloride's got an electronegativity difference around 1.2 or so. That is a polar bond. That is no longer ionic. And now that it isn't ionic, look what happens. It's not a solid anymore. Now it's a liquid. Because super, super big differences in electronegativity give you solids. Pretty much all ionic compounds are solids because there's that big, big difference. When we start to lower the difference in electronegativity, we go from being a solid now to being a liquid, a polar liquid, like water, but a liquid. And we keep going. So we keep going to phosphorus chloride and sulfur chloride. And so that electronegativity difference is going down and down. And now you can see liquid, 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 no longer conducting electricity because there's no ionic character whatsoever. And now, something we'll learn about a little bit later, the vapor pressure starts to increase. It starts to become more and more gas-like. And finally, so once we get to element 16, we go to element 17, which is chloride itself. And so chlorine bonding with chlorine, there's now no difference in electronegativity. It's a completely nonpolar compound, and it goes from being a polar liquid to being a nonpolar gas. Okay, so you can see huge difference in the physical characteristics of all these compounds based simply on what the difference in electronegativity is. So you can see that it's a pretty important concept that determines so many physical properties of these compounds. So the ionic bonding model, we kind of know a little, mostly about it. The metal transfers an electron to a non-metal, they both become ionic, whatever, right? But one thing we sort of didn't really talk about much is Coulomb's law. I just want to spend a minute on this because we've been sort of talking a lot in lab and in recitation recently about precipitates, right? We've been forming arsenate precipitates. I'm working on a really evil question for your test that has something to do with precipitation. And so the question is, why do some ionic compounds dissolve in water and some precipitate? And it comes all, whoops, let me go back. It basically all comes down to Coulomb's law. What the hell's Coulomb's law, you're asking yourself, or asking me, or asking somebody in your room. So Coulomb's law basically says that the force between two charged species is dependent on two things. How charged they are. So what's Q is equal to charge. So how charged each one of them is. If they're highly, highly charged, they're going to come together with great force. And if they're close to each other, if they're far away, the force goes down. That's why it's 1 over the distance. If they're really close together, it's very strong. So that's why sodium chloride dissolves in water. It's basically